Look up at the night sky on a clear evening, and what do you see? A scattering of stars, perhaps the moon, the familiar constellations that have guided humanity for millennia. It feels peaceful, predictable, almost comforting in its constancy, but that view is an illusion, a tiny, quiet fraction of what's truly happening out there in the vast darkness. Beyond what our eyes can perceive, the universe is alive with activity so strange, so spectacular, and so utterly baffling that it makes the wildest science fiction seem tame by comparison. We're talking about cosmic mysteries that defy the laws of physics as we know them, objects and events that scientists are only just beginning to understand, phenomena that challenge not only what we see, but what we believe is possible. Welcome, everyone. Today, we're embarking on a journey to the very edges of known space, exploring 25 of the most bizarre, beautiful, and head-scratching discoveries astronomers have made in recent years. From stars that behave in ways they simply shouldn't, to mysterious structures so enormous they rewrite our understanding of scale itself. These aren't just curiosities, they're clues, pieces of a puzzle that is the cosmos, and each one invites us to rethink our place within it. This is more than a list, it's an invitation to witness the universe not as a static picture, but as a dynamic, evolving, and often shockingly violent arena where the rules are still being written. So get ready to have your reality expanded. We'll be diving into cosmic wonders that glow with energies we can't yet explain, mysterious objects that drift between stars leaving scientists utterly stumped, and revelations so profound they don't just add to our knowledge, they shake its very foundations. This is where imagination meets discovery, and by the end of our journey, the night sky will never look the same to you again. Are you ready? Let's begin. Our journey begins with a cosmic fugitive, an object of unimaginable power that has broken all the rules and escaped its celestial home. Imagine a supermassive black hole, an entity so gravitationally dominant that it typically sits at the very heart of a galaxy, holding everything around it in a powerful embrace. Now picture that same colossal force, not as a stationary anchor, but as a renegade hurtling through the intergalactic void at tremendous speed. And in its chaotic wake, it's not leaving destruction but creating brilliant new life. This isn't a scene from a movie, it's a real astronomical discovery that has left scientists both thrilled and deeply perplexed. The Hubble Space Telescope captured this extraordinary event, a supermassive black hole with a mass equivalent to 20 million of our suns racing away from its host galaxy. But the most stunning detail isn't the black hole itself, which of course we cannot see directly, but the incredible trail it has blazed across space. Stretching an astonishing 200,000 light-years from its point of origin, that's a distance twice the diameter of our entire Milky Way galaxy, is a luminous contrail of young, intensely blue stars. These aren't random stars, they are a direct, beautiful, and violent byproduct of the black hole's frantic journey. So how does a gravitational monster known for consuming light become a catalyst for creation? The prevailing theory is a cosmic game of gravitational billiards on an epic scale. Astronomers believe the rogue black hole was once part of a ternary system, 3 supermassive black holes orbiting each other at the center of its home galaxy. When 2 galaxies merge, their central black holes eventually meet and can form a binary pair. But introduce a third black hole from another galactic merger, and the stable system becomes chaotic. In a complex gravitational dance, one of the 3 can be flung outwards at incredible speed, a process known as the slingshot effect. This isn't a gentle nudge, it's an ejection with enough force to escape the gravitational pull of the entire galaxy. As this behemoth was violently ejected, it didn't travel quietly. It plowed through the dense clouds of gas and dust that populate the galactic halo. The tremendous forces at work compressed this material, triggering shock waves and intense pressure that became the perfect nurseries for star formation. The black hole in its flight became an unintended architect, forging a narrow corridor of newborn stars from the very material it was passing through. This challenges our fundamental understanding on two fronts. First, it upends the classic model of a sedentary supermassive black hole as a galactic centerpiece. They can, it seems, be evicted. Second, it reveals a new and unexpected mechanism for star formation, one driven not by the gentle collapse of a gas cloud, but by the violent, disruptive passage of the universe's most extreme objects. This single observation forces us to reconsider the life cycle of galaxies and the dynamic, often chaotic relationships between their most massive components. It suggests that such galactic ejections might be more common than we ever thought, especially in the early universe when galaxy mergers were frequent. That streak of blue light is more than just a pretty picture. It's a fossil record of a dramatic escape, a clue written in starlight that is reshaping our theories of how galaxies live and evolve. If the rogue black hole made us question the rules within galaxies, our next discovery challenges a principle that governs the entire cosmos. We have long operated under a fundamental assumption known as the cosmological principle. It states that on a sufficiently large scale, the universe is homogeneous and isotropic, a fancy way of saying it should look roughly the same in every direction, with matter spread evenly throughout the cosmic expanse. It's the idea that there are no special places in the universe, no grand structures that make one region fundamentally different from another. This principle is the very bedrock upon which our modern understanding of cosmology is built, a foundation supporting everything from the Big Bang theory to the fate of the cosmos. But what if that foundation is starting to crack? Enter the Giant Arc, a colossal arrangement of galaxies, galaxy clusters, and intergalactic gas that defies this core assumption on an almost unimaginable scale. Discovered by astronomers led by Alexia Lopez at the University of Central Lancashire, this structure isn't just large, it is monumentally, perplexingly vast. Stretching an incredible 3.3 billion light-years across, it is so enormous that it would take a beam of light, the fastest thing in the universe, over 3 billion years to travel from one end to the other. To put that into a human perspective, this single structure spans roughly 1/15 of the observable universe. Its scale is so grand it should be impossible. Its discovery was anything but straightforward. You can't just point a telescope at the sky and see it. The Giant Arc was revealed through a painstaking analysis of the light from distant quasars, the intensely bright cores of active galaxies. As this light travels billions of years to reach us, it passes through clouds of magnesium gas associated with other galaxies and clusters. By mapping where these absorptions occur across a huge swath of space, researchers began to trace a faint giant skeleton. They saw a curve, a vast, symmetrical arc of material hanging in the deep sky, a pattern emerging from the cosmic noise, and this is where the real mystery begins. Our best models of the universe's evolution, based on the prevailing theory of the Big Bang and dark energy, set a theoretical limit on how large structures can grow. The universe simply hasn't existed long enough for gravity to pull matter together into a single, coherent structure of this magnitude. The theoretical size limit is calculated to be around 1.2 billion light-years. The Giant Arc, at nearly 3 times that size, shatters that limit. It shouldn't be there. Its very existence suggests that either our models of the universe's infancy and growth are incomplete, or that the cosmological principle itself is flawed. We might not be living in a truly uniform universe after all. We might be in a universe that can possess preferred directions and structures on the grandest of scales. The implications are profound. This isn't just about adding a new object to the cosmic map. It forces a potential paradigm shift in cosmology. If such giants exist, it could point to exotic physics in the early universe, perhaps unknown influences of dark matter or dark energy that guided the formation of structure in ways we don't yet comprehend. It invites us to consider that the universe might have an inherent architecture, a skeleton of sorts, with threads and walls woven into the fabric of space-time on scales we are only beginning to detect. The Giant Arc is more than a list of galaxies. It is a question mark etched across the sky, challenging us to reconsider the universe's deepest nature. While the rogue supermassive black hole we just discussed is a spectacularly violent escape artist, our next discovery brings the mystery of these dark objects much closer to home, proving that not all cosmic fugitives are galactic in scale. For the very first time, astronomers have confirmed the detection of an isolated stellar mass black hole adrift in the void between the stars of our own Milky Way. This was no simple feat. It was a decades-long cosmic detective story that required observing the invisible by its most subtle effect on the visible, a phenomenon predicted by Einstein himself. This solitary wanderer was discovered through an effect called gravitational microlensing. According to Einstein's theory of general relativity, a massive object warps the fabric of space-time around it. When such an object passes almost directly between Earth and a distant background star, this warped space acts like a lens, bending and focusing the light from the background star. From our viewpoint, the star temporarily appears to brighten, sometimes for just a few hours or days, in a very specific and predictable pattern. This is the telltale signature of a massive, compact object drifting through the galaxy. For years, thousands of these microlensing events have been detected, but the crucial question remained: was the lensing object a dim star, a neutron star, or the elusive solitary black hole? Distinguishing between them became the ultimate challenge. This is where the Hubble Space Telescope entered the investigation. While ground-based surveys can detect the initial brightening of a microlensing event, confirming the nature of the object causing it requires incredibly precise measurements over many years. Hubble's sharp vision was tasked with a painstaking mission to measure the tiny astrometric shift of the background star's apparent position in the sky. As the invisible black hole moved through space, its gravitational field continued to deflect the starlight. Hubble was able to detect this minuscule wobble, a shift so small it's the equivalent of watching a person in New York appear to move side to side by the width of a dime from the distance of Los Angeles. This precise measurement was the key that unlocked the mystery. By combining the data from the microlensing event's brightness curve with Hubble's measurement of the astrometric shift, astronomers could finally calculate the lensing object's mass. The result was definitive, roughly 7 times the mass of our Sun. This mass is far above the limit for a white dwarf or a neutron star, confirming beyond any doubt that the lens was indeed a black hole. Further analysis revealed this particular wanderer is traveling at a respectable speed of about 160,000 kilometers per hour, and it's located approximately 5,000 light-years away from us within the galactic disk. The existence of this solitary black hole opens a profound new window into the demographics of our galaxy. Stars massive enough to become black holes often live in binary systems, but this discovery proves that a significant number are born solo or are kicked out into isolation by the violent forces of a supernova explosion. Its detection suggests that there could be a vast, unseen population of these dark ghosts, perhaps 100 million of them, drifting silently through the Milky Way. Each one is a relic of a massive star that lived and died, its presence now only betrayed by the fleeting distortion of starlight. This confirmation moves these objects from theoretical predictions to observable realities, giving us our first clear census data for the invisible residents of our cosmic neighborhood. But if the discovery of isolated black holes gave us a new census of invisible objects within our galaxy, our next discovery reaches across the deepest of time, challenging the very story of how the universe built its first structures. The James Webb Space Telescope was designed to be a time machine, to peer back further than any instrument before it and witness the dawn of the first galaxies. It has succeeded beyond our wildest dreams, but in doing so, it has presented us with a puzzle so profound that it has thrown the field of cosmology into a state of excited and slightly unnerving crisis. The telescope's first deep-field images were expected to show the infant universe faint, small, chaotic collections of stars just beginning to coalesce. Instead, Webb revealed galaxies that looked like thriving cosmic metropolises. Among them was an object designated Glass Z13, a galaxy that appears to have formed a mere 300 million years after the Big Bang. In the grand timeline of the universe, which is 13.8 billion years old, this is akin to looking at a photo of a human toddler who has already graduated from university. The galaxy is not just present, it is massive, mature, and seems to have already formed a tremendous number of stars in an impossibly short amount of time. The problem lies in the sheer mass and complexity of these objects. Our prevailing model of cosmic evolution, known as the lambda cold dark matter model, provides a detailed and largely successful recipe for how the universe grew from a smooth, hot soup of particles into the web of galaxies we see today. This process takes time. Gravity needs to slowly pull together clumps of dark matter, which then attract ordinary gas, which then eventually cools and collapses to form the first stars, which then gather into the first protogalaxies. These early structures should be small, faint, and relatively simple. Webb's galaxies, however, are colossal and appear fully formed. It's as if we walked into a theater just minutes after the movie started and found the plot already at its climax. This has left cosmologists with a set of deeply uncomfortable yet thrilling possibilities. The first option is that our understanding of galaxy formation is fundamentally flawed. Perhaps some unknown, ultra-efficient process allowed these early galaxies to form stars at a rate hundreds of times faster than we thought possible, converting nearly all of their available gas into stars in a single, furious burst of creation. Maybe the seeds of these galaxies, the initial clumps of dark matter, were far larger and formed much earlier in the universe's history than our models predict, giving them a colossal head start. The second, and even more radical, possibility is that our measurements of the universe's age are wrong. Could the universe be older than we think? This would provide the extra time needed for these galaxies to grow to such immense sizes. However, the age of the universe is not a standalone number. It is intricately tied to our measurements of the Hubble constant and the entire Big Bang model. Tinkering with it would send ripples of confusion through every other area of cosmology, from the behavior of dark energy to the formation of the cosmic microwave background. It's a foundational pillar that few are willing to dismantle lightly. A third, more speculative idea suggests we might be seeing not the first generation of stars, but the second. The very first stars, known as population 3 stars, are theorized to have been monstrously large, brilliant, and short-lived. If they formed and died in cataclysmic supernova extremely quickly, their ejected material could have provided the enriched fuel for a second, incredibly rapid wave of star formation, building up these massive galaxies in record time. Yet even this theory requires pushing physics to its absolute limits. What makes this a true crisis is the consistency of the data. Glass Z13 is not a solitary outlier. Webb is finding dozens of these massive, mature galaxies in the universe's infancy. They are becoming a pattern, a new normal that our old models simply cannot account for. This isn't a case of a single contradictory observation. It is a systematic tension between theory and reality. It means that somewhere in our chain of reasoning, from the physics of star formation to the nature of dark matter or the very expansion history of the cosmos, there is a missing link, a piece of the puzzle we have not yet even imagined. The James Webb Space Telescope was built to provide answers, and it has. But those answers have come in the form of a beautiful, brilliant, and deeply challenging question. While the James Webb's discoveries force us to rewind the cosmic clock and question the universe's earliest moments, another revelation brings our focus to the final, dramatic acts of stellar life, revealing a class of stars that have been hiding in plain sight. Deep in the crowded, ancient heart of our Milky Way, astronomers have uncovered a population of pensioner stars behaving in a way no one predicted. They are the old smokers, and their strange, hushed eruptions are quietly rewriting the story of how the building blocks of planets and life itself are scattered across the galaxy. Imagine a star in its final years, a massive red giant having exhausted the hydrogen fuel in its core. For decades, we've categorized such aging stars into known types, like Mira variables or spectacular supernova progenitors. The old smokers, however, belong to a new category entirely. For most of their lives, they appear utterly normal and unremarkable, quietly glowing. Then, without any clear warning, they undergo a profound transformation. Over a matter of months, they begin to dim dramatically, fading until they are almost 100 times less luminous, nearly vanishing from view. This isn't a quick flicker. This deep dimming can last for years, even decades, before they just as mysteriously return to their former brightness. It's as if the star is drawing a veil of cosmic smoke across its face. What causes this extraordinary behavior? The key is in the name Old Smoker. These stars are believed to be expelling enormous clouds of smoke and dust directly from their surfaces. During their dormant phases, material builds up in their outer atmospheres. Eventually, some unknown trigger causes them to belch out this accumulated matter in a thick, obscuring cloud. Unlike the explosive, violent ejection of a supernova, this is a slower, more ponderous process, a stellar cough that shrouds the star in its own exhaust. This smoke isn't like anything on Earth. It's a complex brew of silicate grains, carbon, and other heavy elements forged in the star's fiery core, now being cast out into the void. This discovery is far more than just a new stellar oddity. It has profound implications for one of astronomy's longest-standing questions, the problem of galactic chemical enrichment. We've long known that the universe began with only hydrogen, helium, and a trace of lithium. Every other element in the periodic table, the iron in our blood, the calcium in our bones, the oxygen we breathe, was forged inside stars and then scattered into space to form new generations of stars, planets, and people. But for years, there has been a discrepancy between the amount of heavy elements we see distributed throughout galaxies and the amount our models said should have been delivered by known sources like supernova and stellar winds. A significant portion of this cosmic inventory seemed to be missing its supplier. The old smokers may well be that missing source, located predominantly in the crowded galactic center, where stars are most densely packed. These elderly giants are perfectly positioned to act as efficient distributors of enriched material. Their eruptions are not violent enough to blast matter out of the galaxy entirely. Instead, they release their smoky clouds at relatively slow speeds, allowing the processed elements to drift gently into the interstellar medium, enriching the surrounding gas clouds from which new stars and planetary systems will eventually form. This provides a steady, gentle drizzle of heavy elements, complementing the violent, punctuated delivery of a supernova. Finding these stars required a special kind of patience and a new way of looking at the sky. The discovery was made using the Visible and Infrared Survey Telescope for Astronomy, or VISTA, in Chile. This telescope conducted a monumental decade-long survey, repeatedly imaging the same crowded star fields near the galactic center. By comparing these images over many years, astronomers could slowly pick out the telltale, gradual dimming of the old smokers amidst the millions of other stars. It was a needle in a haystack search that ultimately revealed an entire hidden population, proving that sometimes the most profound cosmic secrets are not revealed in brilliant flashes, but in the slow, patient dimming of a light. While the James Webb's discoveries challenge our view of cosmic beginnings and the old smokers reveal a hidden phase of stellar life, our next phenomenon presents a mystery of an entirely different nature, one that exists not in the far reaches of time or the crowded galactic center, but in the vast, empty plains between galaxies. Imagine astronomers meticulously scanning the sky with one of the world's most sensitive radio telescopes, expecting to catalog the usual suspects, distant galaxies, pulsars, supernova remnants, when they stumble upon something utterly unexpected: faint, perfect circles of radio emission hanging in the void. These aren't small smudges, they are enormous rings, some so vast they could comfortably contain entire galaxies within their boundaries. Even more bizarre when they point optical, infrared, and X-ray telescopes at the exact same coordinates, they see nothing. No visible source, no heat signature, no high-energy radiation. It's as if these cosmic ghosts are whispering only in a single, low-frequency register of the electromagnetic spectrum, refusing to reveal themselves in any other light. They were officially named Odd Radio Circles, or ORCS, but their elusive nature quickly earned them the more poignant nickname, Orphan Radio Circles, because they appear to have no parent source, no home to call their own. The scale of these structures is almost incomprehensible. A typical ORC can span over 1 million light-years across. To put that into perspective, our entire Milky Way galaxy is a mere 100,000 light-years from end to end. A single one of these rings could contain a dozen galaxies like our own with room to spare. Their discovery was made possible by the Australian Square Kilometre Array Pathfinder, or a SKAP, a radio telescope designed to conduct an all-sky survey with unprecedented speed and sensitivity. Its wide field of view allowed it to capture these faint, diffuse objects that previous, more narrowly focused radio surveys had simply missed. The initial reaction among astronomers was a mixture of excitement and profound confusion. The first instinct was to assume they were familiar objects seen from an unusual angle, perhaps the spherical shockwave from a supernova remnant, but that idea was quickly dismissed. No known stellar explosion could produce a shockwave of such immense proportions. Another thought was that they might be the lobes of radio galaxies, where supermassive black holes eject jets of material far into intergalactic space. But those lobes are almost always paired and connected to a visible galactic core by a central jet. The ORCS are isolated, symmetrical, and most critically, lack any visible central engine. Faced with a complete lack of conventional explanations, scientists have been forced to consider far more exotic possibilities. One leading theory suggests these circles could be the immense shockwaves from a cataclysm of almost unimaginable power, perhaps the merger of two supermassive black holes. When such colossal objects spiral together and finally collide, they release a titanic burst of gravitational waves. It's possible that this event could also trigger a corresponding explosion in the surrounding intergalactic gas, creating a spherical shockwave that expands outward for eons, visible only as a faint ripple in radio waves. Another, even more dramatic, idea posits that an ORC could be the throat of a wormhole. According to some theoretical models, a traversable wormhole might be surrounded by a sphere of concentrated radio waves, and if we were to look down one end, it might appear as a perfect circle. While this is a thrillingly science fiction-like concept, it remains highly speculative, as the actual existence of such large, stable wormholes is purely theoretical. A more recent and promising theory connects these orphan circles to a specific, violent event within a galaxy that is itself now invisible to us. This model, known as the stingray theory, proposes that a powerful galactic wind, driven by a period of intense star formation or a central black hole, could blow a bubble of hot gas out into the surrounding medium. If that central galaxy then suddenly and dramatically quieted down, if its star formation ceased or its black hole turned off, the galaxy would fade from view, leaving behind only the expanding, fading radio bubble as a fossil of its past activity. This would explain the orphan nature. The parent galaxy is still there, but has become too dim for our telescopes to easily detect against the blackness of space. What makes the ORCS so captivating to scientists is that they don't just represent a new class of object, they represent a new kind of puzzle. They are a reminder that our inventory of the cosmos is still incomplete, that there are entire categories of phenomena lurking in the darkness that we haven't even begun to classify. They defy the very process of scientific deduction, resisting all attempts to fit them neatly into existing boxes. They force innovation, demanding new theories and perhaps even new physics to explain their silent, circular presence. Each one is a celestial koan, a riddle written in radio waves, challenging us to expand our understanding of what is possible in the dynamic and often violent ecosystem of the universe. Just when we thought we had the life cycles of stars neatly mapped out, the universe delivers a stunning reminder that even the most well-studied objects can hold breathtaking secrets. For decades, the Boomerang Nebula was a record holder in our cosmic almanacs, celebrated as the coldest known natural place in the entire universe. Located about 5,000 light-years away, this iconic object was a textbook example of a protoplanetary nebula, a brief, 1,000-year phase in a star's life where it transitions from a red giant to a white dwarf, shedding its outer layers in a beautiful, often symmetrical display. Based on initial images from the Hubble Space Telescope, its name seemed perfectly fitting. It appeared to have a distinct, elegant hourglass shape, a twin-lobed structure of outflowing gas that resembled a cosmic boomerang frozen in the void. But as is so often the case in astronomy, a deeper look with more powerful technology revealed that our initial perspective was incomplete, a mere silhouette of a far more complex and fascinating reality. The revolution in our understanding came from the Atacama Large Millimeter/Submillimeter Array, or ALMA, a collection of 66 radio antennas perched high in the Chilean desert. Unlike optical telescopes like Hubble, which see visible light, ALMA observes the universe at millimeter wavelengths. This allows it to peer through obscuring dust and gas to see the colder, denser molecular material that is invisible to other instruments. When astronomers pointed ALMA's incredible resolution at the Boomerang Nebula, the simple hourglass shape vanished. In its place, they saw something entirely different and far more dynamic, a broad, flaring disk of frigid gas stretching far into space. This new structure completely rewrites the story of the nebula's formation. The previous hourglass model suggested a relatively simple, bipolar outflow, jets of gas shooting out from the poles of the dying star. The ALMA data reveals a much more violent and chaotic history. The central star is a red giant in its death throes, and it isn't shedding its atmosphere gently. It is ejecting mass at a ferocious rate, over 100 times faster than similar stars. This incredibly rapid expulsion has created a vast reservoir of cold gas that expands outward, forming the newly seen disk. The iconic boomerang wings that Hubble saw are now understood to be merely a trick of the light, a much smaller, brighter lobe of gas glowing in starlight and buried deep within this much larger, darker reservoir of cold molecular gas. It's like seeing the tip of an iceberg and suddenly discovering the true, massive expanse of ice hidden beneath the water's surface. This revised structure also solves the profound mystery of the nebula's record-breaking cold. The temperature in the outer regions of this expanded disk has been measured at an almost unimaginably frigid 1 Kelvin. That is just a single degree above absolute zero, the theoretical point where all atomic motion ceases. This is even colder than the natural background temperature of the universe, which is a steady 2.7 Kelvin, the lingering afterglow of the Big Bang known as the cosmic microwave background. How can one object be colder than the coldest thing that permeates all of space? The answer lies in the physics of a rapidly expanding gas. The same principle that makes a can of compressed air feel cold to the touch after use is at work here, but on a cosmic scale. As the gas from the dying star erupts outward and expands at tremendous speed, it must do work to push against the surrounding interstellar medium. This rapid expansion cools the gas down, much like the contents of an aerosol can cool as they expand and are released. The Boomerang Nebula's ejection is so rapid and so massive that this cooling effect has become dramatically efficient, dropping its temperature below that of the cosmic background itself. It's a cosmic refrigerator, with the expanding gas acting as the refrigerant, actively chilling itself to a temperature lower than its surroundings. This makes it the only known object in the universe that can truly be described as colder than deep space. The implications of this new shape and its formation mechanism are profound. It suggests that the transition from red giant to white dwarf is not always a graceful, symmetrical process. It can be a messy, explosive, and highly energetic event that carves out vast and complex structures in the interstellar medium. The Boomerang Nebula is no longer just a static, pretty picture. It is a snapshot of a violent and active stellar death, a fleeting moment of extreme physics frozen in time. It teaches us that the universe's record breakers are often not what they first appear to be, and that true understanding requires us to look at the cosmos through every possible lens, from the visible to the submillimeter, to see the full, magnificent picture. While we often look to the depths of the galaxy for interstellar visitors, it turns out one such traveler may have already come to us, colliding with our planet years before we even knew to look for it. The story begins not with a telescope but with a database. In 2019, Harvard astronomers Amir Suraj and Professor Avi Loeb were sifting through a catalog of meteor impacts recorded by U.S. government sensors originally designed to detect nuclear detonations. Their search was for something specific, objects moving at hyperbolic trajectories, speeds so fast they could only mean the object was not gravitationally bound to our sun. Buried in the data, they found an extraordinary candidate, designated CNEOS 2014-0108. This 1-meter-wide object had slammed into the atmosphere off the coast of Papua New Guinea on January 8, 2014. But its most staggering feature was its speed. It was traveling at an incredible 45 kilometers per second relative to the Sun, while it was still far from Earth's gravitational influence. This velocity was so extreme that when you calculated its path backwards, it became clear this rock was not from around here. It was moving too fast to be captured by the Sun's gravity, meaning it was a true interstellar vagabond passing through our solar system from the vast space between stars. The implications were staggering. This meant the first known interstellar object to visit our solar system wasn't the pancake-shaped Oumuamua discovered in 2017. It was this small meteor arriving 3 full years earlier. But a discovery of this magnitude, based on government sensor data, required official confirmation. The velocity reading was the key piece of evidence, and because the sensors are part of a classified network, the exact margin of error for that measurement was also classified. This created a scientific limbo. The researchers were confident in their findings, but a portion of the astronomical community remained skeptical without the full, unclassified data set. For 3 years, the meteor's interstellar status remained an intriguing but unproven hypothesis. Then, in April 2022, the United States Space Command issued an official memo. It stated, and I quote, "The velocity estimate reported to NASA is sufficiently accurate to indicate an interstellar trajectory." This was not just a casual comment, it was a formal confirmation from the Department of Defense, backed by additional analysis from other government agencies. The memo effectively closed the debate. CNEOS 2014-0108 was officially our first known interstellar visitor. Yet, this confirmation was only the beginning of a much deeper and more controversial mystery. The government sensor data didn't just record the object's speed, it also recorded the unusual strength of the material that made up the meteor. As it tore through our atmosphere, it withstood immense pressures before finally disintegrating. The data suggested a material strength far tougher than that of typical iron meteorites common in our own solar system. In fact, its durability was off the charts, ranking it as one of the toughest meteors ever recorded. For Professor Loeb, this extraordinary strength hinted at a possibility that was, to put it mildly, paradigm-shifting. Could this object, he posited, not be a random rock, but a piece of advanced technology manufactured by an intelligent civilization from another star system? He argued that its unique material composition might be evidence of an artificial alloy, something engineered rather than forged in the chaotic belly of a protoplanetary disk. This bold hypothesis, while met with intense skepticism from many mainstream scientists, sparked a tangible, real-world response. In 2023, Professor Loeb led $1 million expedition to the calculated impact zone in the Bismarck Sea. Using a magnetic sled, his team painstakingly dragged the seafloor nearly 2 kilometers down, searching for tiny spherules, molten droplets that would have been created as the meteor vaporized. Astonishingly, they recovered hundreds of these microscopic spheres. Initial analysis revealed a highly unusual elemental composition, with an abundance of certain metals like beryllium, lanthanum, and uranium in patterns not seen in any known solar system meteorites or asteroids. The team dubbed this unique blend Be-la-You spherules. The scientific community remains deeply divided on what these findings truly mean. Critics argue that the composition, while unusual, could still be explained by natural processes we don't yet fully understand, perhaps from a planet with a very different geological history than our own. They caution that the magnetic sled could have collected contamination from human industrial activity or even particles from nuclear testing that occurred in the region decades ago. The debate is fierce and ongoing, a classic scientific tug of war between extraordinary evidence and the requirement for extraordinary proof. Regardless of the ultimate conclusion, the saga of CNEOS 2014-0108 has fundamentally altered our perspective. It proves that interstellar material is not only passing through our solar system, but is occasionally landing right on our doorstep. It demonstrates that we don't necessarily need giant telescopes to find pieces of other star systems. Sometimes we just need to look in our own backyard, or in this case, at the bottom of our ocean. This meteor, whether a singularly strange rock or something far more profound, has opened an entirely new field of astronomy, interstellar archaeology. It is the first fragment of another star we may ever hold in our hands, a silent messenger that journeyed across light years of emptiness to deliver its secrets, one way or another, to us. Moving from the interstellar to the intimately local, our next discovery takes us to the asteroid belt, a region often thought of as a simple collection of primordial rubble. It was here that a planned test of a deep space probe's tracking system unveiled a cosmic Russian doll, an arrangement of objects so perfectly bizarre it seemed almost too good to be true. The Lucy spacecraft, named for the famous hominin fossil, and on a historic mission to study the Trojan asteroids that shared Jupiter's orbit, needed to practice locking onto a small, fast-moving target. For its first test, NASA chose a humble main belt asteroid called 1524 Dinkynish, an Amharic word meaning "you are marvelous." The name, it would soon turn out, was a stunning understatement. As Lucy closed in on Dinkynish, its cameras began to resolve the target. The initial images confirmed it was a small asteroid, roughly 700 meters across, just as expected. But then, something extraordinary happened. A tiny dot of light appeared next to it. Dinkynish wasn't alone. It had a small moon in orbit around it. The team had accidentally discovered a binary asteroid system. This was already a fantastic bonus, a chance to study the dynamics of a tiny two-body system. But as Lucy got even closer, the smaller moon, named Selam, came into sharper focus, and the real marvel revealed itself. Selam wasn't a single, solid rock. It was a contact binary, two distinct lobes that had gently come together and stuck, forming a celestial peanut. This meant Lucy was looking at a binary system where the smaller component was itself a binary, a nested system of 4 objects in total. This configuration is a goldmine for planetary scientists because it acts as a preserved record of the solar system's earliest days. The dominant theory for how such systems form is through a process called the Yorp effect. As a small, irregularly shaped asteroid spins under the sunlight, the uneven heating and subsequent re-radiation of that heat as infrared energy creates a tiny but constant torque. Over millions of years, this torque can slowly spin the asteroid up until its rotational velocity overcomes its own gravity. At that critical point, loose regolith and even large boulders on its surface can be flung into space. If the asteroid is a loose rubble pile, which many small asteroids are, the entire structure can destabilize, and a significant portion of it can be shed. This ejected material doesn't just fly off into space. It remains gravitationally bound in a cloud of debris that slowly coalesces into one or more moons. In the case of Dinkynish, it appears a chunk was shed, and that chunk itself was likely made of two smaller pieces that gently drifted together to form the contact binary we now call Selam. The discovery of Selam's unique shape provides crucial supporting evidence for this entire formation model. It suggests that the forces at play during the formation of these tiny moons are incredibly gentle. The two lobes of Selam came together at a speed of perhaps only a few meters per second, a leisurely walking pace. Any faster, and they would have shattered each other or bounced apart. This slow, delicate dance points to an environment where gravity is the dominant force, not violent collisions. It's a window into the fundamental processes that built our planets. In the early solar system, dust grains collided gently to form pebbles, pebbles formed rocks, and so on, in a hierarchical process known as accretion. Selam is a frozen snapshot of this very process, but on a much larger scale and happening billions of years after the planets themselves had finished forming. The implications of this one lucky observation ripple far beyond this single asteroid pair. It strongly suggests that such complex multi-body systems could be incredibly common throughout the asteroid belt and beyond. If a quick flyby of a random asteroid can reveal such an intricate structure, then our previous census of simple, solitary asteroids was likely a vast oversimplification. The small body population of our solar system is probably teeming with binaries, contact binaries, and even more complex arrangements that we simply haven't had the resolution to see until now. This changes how we model the evolution of the asteroid belt, how we assess the potential hazards of near-Earth objects, and perhaps most importantly, it gives the Lucy mission team immense confidence as they head toward the Trojans. If a simple instrument test could reveal a system this marvelous, what other breathtaking wonders are waiting for us in the depths of space, just out of sight until we look closely enough? But for all the incredible discoveries made by telescopes and spacecraft studying distant stars and galaxies, some of the most profound revelations are happening right next door on the rusty surface of our planetary neighbor. The Perseverance rover's mission in Jezero crater was built on a powerful hypothesis that this specific patch of Mars was once the site of a sprawling lake fed by a winding river delta. It was chosen as the perfect place to not only look for signs of past habitability, but to collect samples that might one day hold the answer to one of humanity's oldest questions. And now the data is in, and it has delivered a discovery that far exceeds even the most optimistic predictions. Perseverance has struck a bonanza, uncovering a stunningly diverse suite of organic molecules preserved within the ancient rocks of that very delta. It's crucial to pause here and clarify a term that often causes excitement to leap ahead of the evidence. In astronomy, the word organic has a very specific and more limited meaning than in everyday conversation. It does not mean comes from life. Instead, it refers to molecules that are primarily based on carbon and often include hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are the fundamental building blocks of life as we know it, the chemical Lego pieces from which proteins, DNA, and cell membranes are constructed. Finding them on another world means that the fundamental chemistry required for life was present and active there. It doesn't prove life existed, but it proves the potential was undeniably there. The rover's onboard instrument, nicknamed Sherlock, has been acting as a supremely sophisticated chemical detective. By using lasers and spectrometers, it can scan a rock target and identify the unique spectral fingerprints of different molecules. The results from multiple samples drilled from different layers of the delta have revealed an astonishing variety. Scientists are detecting signatures consistent with aromatic hydrocarbons' complex ring-shaped carbon structures, as well as compounds linked to sulfates. This diversity is the key finding. It suggests that multiple geological processes and potentially even different ancient environments were at work to create and preserve this chemical soup. It wasn't a one-off event. It appears to have been a persistent, ongoing phenomenon in Jazero's ancient past. The environment these molecules were found in makes the discovery all the more compelling. Perseverance is not exploring a random, bland plain. It is meticulously driving through the geological remains of a river delta. The rocks it is sampling are mudstones and sandstones, fine-grained sediments that were precisely the type of material that settled quietly to the bottom of a still lake billions of years ago. On Earth, such sedimentary layers are renowned for preserving fossils and chemical evidence of ancient life because they form in calm, protective environments that shield organic material from the destructive radiation and oxidation found on the surface. The rover has found that the Jezero rocks contain iron-rich carbonate, a mineral that is exceptionally good at encapsulating and preserving delicate organic compounds for eons. Essentially, Perseverance has located the perfect natural time capsule, an ancient Martian lakebed with precisely the right chemistry to entomb and safeguard these fragile building blocks. This combination of factors, the stunning diversity of the molecules and the ideal, life-preserving environment they were found in, makes this the most compelling evidence yet that Mars was not only habitable but was actively prepped for life. It had the right ingredients mixed in the right kitchen and stored in the right pantry. The planet appears to have had a complex organic geochemical cycle, one that could have provided a steady supply of these critical compounds. Whether this chemical symphony ever culminated in the actual emergence of life is the next great mystery, one that the collected samples are intended to help solve when they are eventually returned to Earth. For now, the message from Jezero Crater is clear and profound. Mars was a world that played by the same chemical rules as early Earth, assembling the very pieces that, here at least, eventually learned how to come alive. For generations, one cosmological truth has been considered so fundamental it's practically gospel. Galaxies are built upon a hidden foundation of dark matter. This mysterious, invisible substance is believed to be the universe's primary architect, providing the gravitational scaffolding upon which ordinary matter could coalesce into the brilliant structures we see. Without this dark matter halo, our models insist, a galaxy could never form in the first place, and it would quickly fly apart from the centrifugal force of its own rotation. This isn't a fringe idea. It is the absolute cornerstone of the lambda cold dark matter model, the prevailing theory of our universe, which is why the discovery of galaxies that appear to be completely devoid of this essential ingredient sent such a profound shockwave through the world of astronomy. It was like finding a ship effortlessly sailing across the ocean with no hull beneath the waterline. The story centers on a strange class of galaxies known as ultra-diffuse galaxies. As their name implies, these are ghostly, wispy collections of stars, often as large as the Milky Way but containing only about 1% of its stars. They are cosmic phantoms, vast and faint. Among them, two galaxies stood out as particularly peculiar, NGC 1052 DF2 and its sibling, NGC 1052 DF4. Initially spotted by the Dragonfly telephoto array, a telescope specifically designed to see these low-surface brightness objects, they were intriguing curiosities. But when a team led by astronomer Pieter van Dokkum at Yale University turned the powerful Keck Observatory toward them to measure their dynamics, they expected to find the telltale signs of a massive dark matter halo. Instead, they found nothing, the key to weighing a galaxy and thus inferring the presence of invisible mass lies in measuring the velocities of objects within it. The faster those objects move, the stronger the gravitational pull holding them in must be, and thus the more mass the galaxy contains. Van Dokkum's team focused on brilliant, compact clusters of stars that orbit within these diffuse galaxies. To their utter astonishment, the star clusters in DF2 were moving remarkably slowly. The math was inescapable. The total mass required to keep those clusters from flying away was almost exactly equal to the mass of the visible stars themselves. There was simply no room left for dark matter. The result was so heretical that the initial reaction within the scientific community was one of intense skepticism. Surely, there must be an error in the measurements, or perhaps we were seeing these galaxies from a strange angle that skewed the data. But further observations, including meticulous studies with the Hubble Space Telescope, only confirmed the initial findings. DF2 and later its neighbor DF4 were for all intents and purposes dark matter-free. This revelation created a paradox that cuts to the very heart of cosmology. If dark matter is necessary for galaxies to form, how do you end up with a galaxy that has none? The discovery didn't just add a new object to the catalog, it punched a hole right through the standard model. Almost immediately, alternative theories began to emerge to solve this impossible puzzle. One compelling idea suggests these galaxies might be the aftermath of a catastrophic collision. Perhaps they were once normal galaxies rich with dark matter that passed through the dense core of a galaxy cluster. In this scenario, the sticky effects of dynamical friction could have stripped away their dark matter halos, while the more compact stars passed through unscathed, leaving behind a ghostly, dark matter-poor remnant. Another fascinating theory involves a completely different formation mechanism. Maybe these galaxies were born not from collapsing clouds of dark matter, but from gas that was violently ejected during a tremendous galactic collision. As this tidal tale of gas expanded and cooled, it could have fragmented and condensed into stars all on its own, creating a galaxy that formed without a dark matter skeleton from the very beginning. The existence of these bizarre objects forces a difficult choice upon cosmologists. Either our understanding of how galaxies form is deeply flawed, or our conception of dark matter itself needs a radical revision. Perhaps dark matter isn't a single, simple particle that only interacts through gravity. Maybe it can interact with itself or with normal matter through other, unknown forces, which could explain how it could be separated out and removed from a galaxy. The discovery of DF2 and DF4 transformed them from astronomical curiosities into critical test cases. They are no longer seen as problems to be explained away, but as natural laboratories for stress testing our most fundamental theories about the universe's structure. Their very impossibility makes them one of the most important discoveries in modern astronomy, a stark reminder that the cosmos always has a way of defying our neatest and most cherished assumptions. Just when we think we've catalogued every type of stellar behavior, the universe delivers another stunning surprise, redefining a class of object we believed we understood perfectly. For over half a century, the term pulsar has been synonymous with one specific type of celestial object, a neutron star. These are the incredibly dense, city-sized cores left behind after a supernova, spinning at dizzying speeds and sweeping the universe with lighthouse-like beams of radiation. It's a textbook definition, one of the most stable concepts in all of astrophysics. That is, until astronomers stumbled upon a system that shouldn't exist, one where a completely different kind of dead star was putting on a pulsar's performance with breathtaking precision. Welcome to AR Scorpii, a binary star system that has rewritten the rules and revealed an entirely new breed of cosmic power plant. Located approximately 380 light-years away in the constellation Scorpius, AR Scorpii seemed at first glance to be a rather ordinary variable star, a system where two stars orbit each other, causing regular dips and brightenings in their combined light. But when astronomers and dedicated amateur stargazers took a much closer look, they found its behavior was anything but ordinary. This system brightens and fades with a rapid clockwork pulse every 1.97 minutes. That's not the gentle waxing and waning of one star eclipsing another. It is a frantic, energetic strobe light flashing across the electromagnetic spectrum, from radio waves all the way up to highly energetic gamma rays. The source of this incredible pulse was the system's white dwarf, a stellar ember about the size of Earth. But this was no ordinary white dwarf. It was behaving like a neutron star, earning it the monumental title of the first ever white dwarf pulsar. The mechanics of this system are a masterpiece of celestial violence and precision. AR Scorpii consists of two stars, a hot, intensely magnetic white dwarf and a cooler, larger red dwarf companion. They are locked in a close orbit, revolving around each other every 3.6 hours. The white dwarf is spinning on its own axis at an unbelievable rate, completing a full rotation every 1.97 minutes. This rapid spin, combined with a magnetic field that is at least 100 million times stronger than Earth's, transforms the white dwarf into a colossal natural particle accelerator, a cosmic T-vatron. As it spins, it generates powerful beams of electrons and other particles, whipping them up to nearly the speed of light. These beams sweep through space like a runaway fire hose, relentlessly pummeling the surface of the hapless red dwarf companion with devastating effect. The result is a spectacular light show. The incoming barrage of high-energy particles heats a large spot on the red dwarf's atmosphere to incredible temperatures, causing it to glow intensely across multiple wavelengths. Because the white dwarf's beam is sweeping around like a lighthouse, we on Earth only see this bright hotspot when it is pointed in our direction. As the beam rotates away, the system appears to dim. This is why the entire binary flashes at us with such metronomic regularity. The period is set by the spin of the white dwarf, not by the orbital period of the two stars. The red dwarf is essentially being used as a cosmic cathode ray tube, its face lit up by the particle beam from its aggressive partner. It's a form of illumination, but one born from a brutal and ongoing assault. The existence of a white dwarf pulsar forces a profound reconsideration of what it actually means to be a pulsar. We previously defined them by their engine, a neutron star. But AR Scorpii argues that the definition should be based on the mechanism, not the object. A pulsar is any spinning, magnetized object that produces a focused, periodic beam of radiation through a process called non-thermal emission. This is a critical distinction. Thermal emission is the glow of a hot object, like a light bulb filament. Non-thermal emission is the radiation generated by particles moving at relativistic speeds in a powerful magnetic field, which is exactly what is happening here. AR Scorpii proves that neutron stars do not hold a monopoly on this physical process. Under the right conditions of spin and magnetic field strength, a white dwarf can replicate the phenomenon perfectly. This discovery unveils a new and extreme evolutionary path for white dwarfs. We typically picture them as quiet, slowly cooling relics destined to fade away into black dwarfs over trillions of years. AR Scorpii presents a dramatically different portrait. It suggests that some white dwarfs can remain phenomenally dynamic and powerful engines long after their death, capable of energetic output that rivals their neutron star cousins. It raises fascinating questions about the origin of its immense magnetic field and incredible spin. Was it born this way from a peculiar supernova, or did it acquire this energy through interactions with its companion star? Finding more systems like AR Scorpii will be key to solving this puzzle. as each one serves as a natural laboratory for studying particle acceleration and magnetism under conditions we could never hope to recreate on Earth. This isn't just a new class of object, it's a new window into the extremes of physics, proving that even the quietest seeming stellar remnants can harbor ferocious and unexpected power. And just as the white dwarf pulsar demonstrates the unexpected violence that can persist in a star's final act, another cosmic farewell reveals an even more intricate and paradoxical dance between death and rebirth. The Hubble Space Telescope has gifted us countless iconic images of the cosmos, but few are as simultaneously beautiful and haunting as that of NGC 2022, a planetary nebula that has earned the fittingly dramatic nickname, the Godzilla Nebula. From our vantage point, it appears as a colossal, glowing eye staring out from the void, its intricate shell of gas illuminated by the tiny, brilliant stellar ember at its very center. This is the final portrait of a star not unlike our own Sun, a snapshot of a gentle death that has, upon closer inspection, revealed a far more complicated and tumultuous story. The classic narrative for a planetary nebula is one of a peaceful, if dramatic, retirement. A star of low to intermediate mass, having exhausted the hydrogen fuel in its core, swells into a red giant. In its final throes, it begins to pulse, gently shedding its outer layers into space over thousands of years. These ejected layers form an expanding shell of incandescent gas, while the star's hot, exposed core, now a white dwarf, remains behind, flooding the nebula with ultraviolet radiation that makes it glow in brilliant colors. It's a beautiful and seemingly straightforward process of a star retiring its atmosphere, leaving its dense core to cool for eternity. For NGC 2022, this was the accepted story. But new, detailed analysis of Hubble's data has uncovered a stunning plot twist in this well-known tale, suggesting the star's death is not a simple one-way journey. The central white dwarf in the Godzilla Nebula is not simply cooling off in quiet isolation. Spectroscopic readings indicate that it might be pulling a remarkable cosmic heist, stealing some of its own expelled material back from the nebula it just created. This isn't a gentle drift, it's a violent act of repossession. As the nebula expands, it doesn't do so as a perfectly smooth shell. Instabilities cause some regions to be denser and clumpier than others. The immense gravity of the white dwarf can gravitationally tug on these denser clumps of gas, pulling some of the material back inward. This creates a temporary, chaotic accretion disk of its own former atmosphere, now spiraling down onto its searingly hot surface. This act of stellar cannibalism has a spectacular and fleeting consequence. When this fallen material, rich in hydrogen, piles onto the surface of the white dwarf, it can, under the right conditions, trigger a final, desperate burst of nuclear fusion. Imagine a fire that has nearly burned out, only for someone to throw a last handful of kindling onto the embers, causing a brief, final flare of light. This is precisely what astronomers suspect is happening within the heart of the Godzilla Nebula. The white dwarf is experiencing a last gasp, a final flare-up of energy as it momentarily reignites the very processes that defined its life. This outburst can flood the surrounding nebula with a new wave of radiation, shock heating the gas and changing its chemical structure, adding another layer of complexity to the nebula's beautiful structure. This process fundamentally changes our understanding of a star's final chapter. It is no longer seen as a simple, linear transition from red giant to inert white dwarf. Instead, it can be a dynamic, feedback-driven loop where the corpse of the star actively interacts with its own funeral shroud. This final burst of fusion is not a rebirth that will save the star. It is a brief and brilliant last stand against the inevitable. It will quickly burn through its stolen fuel, after which the white dwarf will resume its slow, permanent fade into darkness. But for a short while, this dying star gets to shine one last time with the brilliance of its youth, a poignant reminder that even in death, the universe can find moments of spectacular, defiant resurgence. The Godzilla Nebula, with its watchful eye, is not just a monument to an ending, but a testament to the complex, unpredictable, and often recursive nature of stellar evolution. While the White Dwarf Pulsar and the Godzilla Nebula show stars pushing the boundaries of known physics right to the very end, some stars don't get a chance to live out their lives at all. Instead, they are subjected to a gravitational cataclysm so violent it doesn't just end them, it launches their remnants on a one-way trip out of the galaxy itself. These are the hypervelocity stars, and they are some of the fastest-moving objects ever detected in our cosmos, blazing across the Milky Way at speeds exceeding 2 million miles per hour. To put that incomprehensible velocity into perspective, at that rate, you could travel from Earth to the Moon in a mere 5 minutes. They are stellar cannonballs, and for years their origin was one of the galaxy's great mysteries. The answer, it turns out, lies in the most chaotic and terrifying place imaginable, the very heart of our own galaxy, under the influence of its supermassive black hole, Sagittarius, a star. The story of their discovery began with a systematic survey of the sky, where astronomers noticed a handful of stars moving with velocities so extreme they were not just orbiting the galactic center, they were escaping its gravitational pull entirely. Their trajectories were clear. These stars were not visitors from intergalactic space falling inward. By tracing their paths backwards, their point of origin was pinpointed with shocking consistency: the galactic center. This was the crucial clue. Only an object of truly monstrous power could impart such tremendous energy to a star, and at the center of our Milky Way, there is only one object that fits that description: Sagittarius, a star, a supermassive black hole with a mass equivalent to 4 million suns. But how does a black hole, an object famous for trapping everything, including light, become a cosmic catapult that flings stars away? The answer is a brilliant and violent piece of gravitational engineering known as the Hills mechanism, named for the astronomer Jack Hills, who first proposed it. This process doesn't involve a single star falling toward the black hole. It requires a binary pair, two stars locked in a mutual orbit. Imagine this binary system, through its long journey around the galaxy, wandering a little too close to the immense gravitational well of Sagittarius, a star. As the pair is pulled inward, the black hole's tidal forces begin to violently strain their bond. The gravitational pull on the star closer to the black hole becomes exponentially stronger than the pull on its partner. If they cross a critical point of no return known as the tidal radius, the binary bond is shattered. What happens next is a celestial version of a slingshot maneuver, but with unimaginably high stakes. One of the stars is captured by the black hole, pulled into a tight, doomed orbit that will eventually lead to its consumption. Its partner, however, receives the gravitational equivalent of a knockout punch. The immense orbital energy that was once shared between the two stars is suddenly transferred entirely to the one that is set free. It is flung away from the black hole at a significant fraction of the speed of light, like a stone from a sling, now possessing enough kinetic energy to overcome the gravitational pull of the entire Milky Way galaxy. In a single, violent moment, a star that was born in the galactic disk is sentenced to an eternal exile in the intergalactic void. These hypervelocity runaway stars are far more than just fascinating oddities. They are invaluable cosmic probes. Their trajectories are a direct record of the event that created them, carrying forensic information about the environment around Sagittarius, a star. By studying their speed and direction, astronomers can indirectly map the gravitational field of the black hole and better understand the population of binary stars that dare to venture close to the galactic center. Furthermore, the stars themselves are time capsules. As they race through the galaxy, they carry the chemical composition of their birthplace near the core, a region that is otherwise incredibly difficult to observe in detail due to obscuring clouds of dust and gas. Analyzing the light from these stellar fugitives gives us a unique sample of the material that exists in the most extreme environment in the galaxy. the existence of hypervelocity stars confirms that the region around our galaxy's central black hole is a dynamic and violently active arena, a place where the laws of gravity are pushed to their absolute limit. It is a gravitational laboratory where binary systems are torn apart and transformed into high-energy projectiles, some of which are now sailing through the darkness between galaxies, destined to never again know the warmth of a galactic home. They are the silent, high-speed witnesses to the awesome power lurking at the very center of our seemingly serene spiral galaxy. For centuries, our view of the Milky Way has been defined by its most luminous components: the brilliant streak of the disk, the dense bulge at its center, the sparkling star clusters and glowing nebulae. But we now understand this dazzling structure is merely the visible part of a far larger and more massive cosmic entity, one shrouded in an enormous, invisible cloak of searingly hot gas. The first detailed map of this monumental structure has finally been created, revealing the true nature of our galaxy's atmosphere and providing a stunning solution to a mystery that has perplexed astronomers for decades. This breakthrough was delivered by the Extended Roentgen Survey with an Imaging Telescope Array, or eROSITA, an incredibly sensitive X-ray telescope. While optical light shows us the stars, the universe reveals its most energetic processes in the high-energy X-ray part of the spectrum. eROSITA All-Sky Survey was designed to catalog millions of X-ray sources, but its most profound discovery came from what lay between them: a faint, pervasive glow. By meticulously filtering out the bright point sources, astronomers were left with a map of the diffuse X-ray background, and within that faint signal, the ghostly outline of our galaxy's halo emerged into view for the very first time. The structure it revealed is both beautiful and awe-inspiring in its scale. The Milky Way is enveloped in a vast spherical cloud of multimillion-degree gas that extends for hundreds of thousands of light-years in every direction. This isn't a smooth, featureless bubble. The eROSITA data shows it has a complex filamentary anatomy, with tendrils and wisps of hotter and slightly cooler gas woven throughout its structure. These filaments are the key to its origin story. They are believed to be the fossil remnants of the galaxy's violent formation, the scars left behind as smaller galaxies were cannibalized and their gaseous contents were heated to incredible temperatures as they plunged into the growing gravitational well of the young Milky Way. Other filaments may be the result of opposite processes: outflows from supernova explosions and the galactic center, ejecting material out into the halo where it is heated and joins the reservoir. This map shows our galaxy not as a static island, but as a dynamic, breathing entity, constantly interacting with its extended atmosphere. Beyond its breathtaking structure, this discovery solves one of the most stubborn problems in modern cosmology: the case of the missing baryons. Baryons are the ordinary matter that makes up everything we can see: stars, planets, gas, and dust. When cosmologists add up all the ordinary matter they can account for in the modern universe and compare it to the amount they know was created in the Big Bang, a significant fraction, nearly half, has been unaccounted for. This missing matter wasn't truly gone. The leading theory was that it must be hiding in a diffuse, hard-to-detect web of warm, hot gas stretching between galaxies. The eROSITA map of the Milky Way's halo provides the first direct, local evidence for this theory. The immense mass of hot gas it has mapped accounts for a huge portion of the baryons that should be associated with our galaxy but had never been found. It turns out the missing matter was right over our heads all along, too hot to see in visible light but glowing faintly in X-rays, waiting for an instrument like eROSITA to finally reveal it. This halo is far more than a historical relic or a solution to an accounting problem. It plays a critical role in the galaxy's ongoing life cycle and even forecasts its eventual fate. The hot gas acts as a crucial reservoir for future star formation. As it slowly cools, particularly in the denser filamentary regions, it can condense and rain back down onto the galactic disk, providing the fresh fuel needed to birth new generations of stars. This process of galactic recycling is essential for sustaining the Milky Way's vitality over billions of years. Yet, this same halo also tells a story of an ending. The gravitational pull of the galaxy is what holds this enormous atmosphere in place. But in the far, far future, as the Milky Way continues to evolve and merge with other galaxies, this grip may weaken. The hot gas could be gradually stripped away, ejected into the intergalactic void, slowly starving the galaxy of the material it needs to make new stars. The magnificent halo that helped build our galaxy and now sustains it may ultimately be the very thing that, once lost, leads to its long, slow fade into darkness. But if the hypervelocity stars and the galactic halo speak to the grand gravitational architecture of the cosmos, our next discovery plunges us into a realm where the very concepts of cause and effect, past and future, begin to dissolve into a bizarre and breathtaking quantum fog. We now venture into one of the most philosophically unsettling experiments ever conceived, one that uses the ancient light from the edge of the observable universe to probe the very fabric of reality, suggesting that a decision made by an experimenter today can ripple backwards in time to influence an event that occurred billions of years ago. This is the domain of the cosmic scale delayed choice quantum eraser, and to understand its profound implications, we must first grapple with one of the most fundamental and weirdest properties of the quantum world. At the heart of this mystery is the dual nature of light and matter. A single photon, a particle of light, can behave as either a compact particle or a spread-out wave, and which one we see depends entirely on how we choose to measure it. In the classic double-slit experiment, if you don't try to determine which of two slits a photon passes through, it behaves like a wave, creating an interference pattern on a screen behind the slits, a signature that it somehow went through both paths simultaneously. However, if you place a detector at the slits to catch it in the act and pinpoint its path, it immediately switches to behaving like a single particle, and the interference pattern vanishes. The act of measurement, it seems, forces the photon to choose a state. This is strange enough, but the delayed choice variant of this experiment pushes this weirdness to its absolute limit. In a lab on Earth, scientists can wait until after a photon has already passed through the slits and is presumably already on its way to the screen to then randomly decide whether or not to obtain which path information. Astonishingly, the results on the screen always correspond to that later choice. It's as if the photon's decision about how to behave at the slits is retroactively changed by the experimenter's future decision to look or not to look. Now take this mind-bending concept and scale it up to a truly cosmic proportion. A team of physicists proposed an experiment that replaces the simple double-slit apparatus with two telescopes on Earth, pointed at a single, incredibly distant quasar. A quasar is the intensely bright core of a distant galaxy, powered by a supermassive black hole, and it emits vast numbers of photons. Because these photons originate from a single, minuscule point billions of light years away, they can serve as the cosmic equivalent of a laser pointer aimed at Earth. The experiment relies on a quasar that is positioned such that its light reaches us by bending around two sides of a massive galaxy or galaxy cluster that lies between it and us, an effect called gravitational lensing. This cosmic lens creates two distinct, separate paths for the light to travel. Just like the two slits in the laboratory experiment, the photons from this quasar have been traveling through the void for billions of years. They embarked on their journey long before our planet even formed, let alone before humans built telescopes and quantum physics laboratories. According to the proposal, these ancient photons would finally arrive at the two telescopes on Earth. The researchers would then use a device called a beam splitter to randomly combine these photons from the two paths or keep them separate. Combining them would, in effect, erase any potential which path information, forcing the photons to display wave-like behavior and show interference. Keeping them separate would allow the scientists to determine which telescopic path each photon took, forcing them to behave like particles with no interference. The staggering implication is this: the random choice made by the beam splitter today would seem to dictate whether these photons, which began their journey billions of years in the past, traveled across the universe as waves or as particles. A decision in our present appears to reach back through time and sculpt the behavior of a particle at the moment of its emission, an event that is, for all intents and purposes, locked in the ancient past. This isn't science fiction, it's a serious, peer-reviewed proposal that uses the universe itself as a grand laboratory apparatus. This cosmic experiment fuels a fierce and ongoing debate about the nature of time and reality. One interpretation is the provocative idea of retrocausality, that effects can precede their causes and the future can influence the past. This radically challenges our everyday classical understanding of time as a strict linear arrow. Another, perhaps even more radical, interpretation is that the universe is not locally real. Real meaning that objects have definite properties independent of observation, and local meaning that influences cannot travel faster than light. The results suggest that reality may not be fixed until it is measured, and that the past itself may not be a settled ledger, but remains fluid until the present moment forces it to assume a specific form. It implies a universe where the distinction between past, present, and future is not fundamental, but may be an emergent property of a deeper, more interconnected quantum reality. The light from that distant quasar, therefore, is more than just a beacon from the early universe. It is a thread woven into the very fabric of a cosmic tapestry where time itself is a tapestry still being woven, its final pattern dependent on choices we have not yet even made. While our quantum experiment with ancient light challenges the very nature of time and reality, another recent mission has provided us with an incredibly tangible, physical artifact from the deep past, one that we can actually hold in our hands and analyze. After a journey of billions of miles and 7 years in space, NASA osiris-rex spacecraft finally delivered its precious cargo to the Utah Desert, a canister containing just over 120 grams of rock and dust collected from the surface of asteroid Bennu. To the untrained eye, it might look like a small pile of black gravel, but to scientists, it is an unparalleled treasure chest, a pristine time capsule that has been sealed and untouched for over 4.5 billion years. The initial laboratory analysis of this material has been nothing short of revolutionary, revealing a world that is not only rich with the raw ingredients for life, but one that fundamentally strengthens our understanding of how our own planet became a living world. The very first tests revealed two components that sent shockwaves of excitement through the scientific community: a stunning abundance of water-bearing clay minerals and a surprisingly high percentage of carbon. Let's break down why these two discoveries are so monumental. The clay minerals, specifically magnesium-bearing phyllosilicates, are compelling because they can only form in the presence of liquid water. This indicates that Bennu's parent body, a much larger world that was shattered in a long-ago impact, was not a dry, inert rock. It was an active, wet world with a complex internal plumbing system where water flowed and interacted with the rock, altering its chemistry. This finding alone transforms our view of asteroids from simple, boring chunks of debris into dynamic, geologically interesting miniature worlds with their own rich histories. Then there is the carbon. The preliminary analysis showed that the sample contains nearly 5% carbon by weight, a concentration far higher than anyone had predicted. Carbon is the absolute backbone of organic chemistry. It's the element that forms the complex, chain-like molecules that are essential for life as we know it. And this isn't just simple carbon. Early analysis has already identified a vast array of complex organic molecules within the sample, including amino acids and nucleic acids. These are the very building blocks of proteins and DNA, the fundamental components from which every living thing on Earth is constructed. Finding them in such abundance on a carbon-rich asteroid like Bennu is like finding a fully stocked kitchen on a deserted island. It doesn't prove someone is there to cook, but it shows that all the necessary ingredients are present and waiting. What makes the osiris-rex sample so uniquely powerful compared to meteorites that fall to Earth naturally is its pristine condition. Meteorites are incredible sources of information, but they are compromised the moment they scream through our atmosphere. The intense heat of entry can scorch away delicate organic compounds and alter the minerals within. They then lie on the ground, exposed to Earth's water and weather, which further contaminates them. The Bennu sample is different. It was collected directly from the asteroid in a gentle 5-second TAG maneuver and then sealed within a protective capsule for its journey home. It has never been touched by Earth's atmosphere or biosphere until it was opened in a pristine, nitrogen-filled curation lab at NASA Johnson Space Center. This means every molecule, every grain of dust, is exactly as it was in the depths of space, offering an uncontaminated view into the early solar system. This level of preservation allows scientists to perform a kind of cosmic archaeology. The minerals and organics within this sample are older than our solar system itself. They are stardust forged in the hearts of ancient stars that died long before our sun was born. By studying their isotopic signatures, the unique chemical fingerprints that reveal their origin, researchers can trace these materials back to their stellar sources, understanding the recipe of the cloud of gas and dust that eventually collapsed to form our sun and planets. The Bennu sample is a direct physical record of that primordial cloud. All of this evidence converges to powerfully support one of the most compelling theories in modern science, panspermia, or more specifically, the idea that asteroids like Bennu could have seeded the early Earth with the very ingredients necessary for life. The young Earth was a violent, molten world, bombarded by countless such asteroids and comets during a period known as the Late Heavy Bombardment. This sample provides the strongest evidence yet that these impacting bodies were not just bringers of destruction, they were also deliverers of destiny. They likely supplied a significant portion of Earth's water, filling our early oceans. And crucially, they rained down upon our planet a rich supply of probiotic material, the complex organic molecules that could have concentrated in warm little ponds or deep sea vents, eventually, through billions of years of chemistry, initiating the chain of events that led to the first self-replicating molecules and ultimately to us. The osiris-rex mission hasn't just brought back rocks from an asteroid. It has brought back a piece of our own ancient history, a testament to our cosmic connectedness and a powerful clue in the eternal quest to understand our own origins. This growing disagreement isn't a simple case of a minor measurement error. It is a full-blown crisis that has only deepened with each new and more precise dataset. On one side of this debate, we have the Planck Space Telescope's exquisite measurements of the cosmic microwave background, the faint afterglow of the Big Bang itself. This ancient light provides a snapshot of the infant universe when it was just 380,000 years old. By meticulously mapping the tiny temperature fluctuations in this radiation, scientists can determine the fundamental ingredients of the cosmos, the amounts of ordinary matter, dark matter, and dark energy with incredible precision. Plugging these values into the standard model of cosmology gives us a prediction for how fast the universe should be expanding today. The Planck measurement yields a Hubble constant value of approximately 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, a unit equal to 3.26 million light-years, a galaxy is moving away from us 67.4 kilometers per second faster. On the other side of the divide, we have the distance ladder method, a step-by-step process that builds a chain of measurements from nearby stars all the way out to distant galaxies. It starts with parallax measurements to nearby stars made by the Gaia spacecraft, which gives us precise distances. We then use those stars to calibrate the brightness of certain types of variable stars called Cepheids, whose pulsation rate is directly tied to their true luminosity. Knowing how bright these Cepheids truly are allows us to find their distance in farther off galaxies. Finally, we use those Cepheids to calibrate the ultimate cosmic distance markers, Type 1a supernova. These stellar explosions are so brilliantly consistent in their peak brightness that they are known as standard candles. By measuring how dim these supernovae appear in very distant galaxies, astronomers can calculate precise distances. When this distance is combined with the redshift of the galaxy, a measure of how much its light is stretched by the expansion of space, we get a direct local measurement of the expansion rate. This painstaking process, championed by the Hubble Space Telescope and now refined by its successor, the James Webb Space Telescope, consistently gives a higher value, around 73 kilometers per second per megaparsec. The difference between 67 and 73 might seem small, but the precision of these measurements is so high that the chance this discrepancy is a mere statistical fluke is less than 1 in a million. It is a real and stubborn problem. This isn't just a quarrel between two telescopes, it is a direct conflict between two ways of seeing the universe. The Planck method looks at the ancient universe and extrapolates forward using our best model, while the distance ladder method measures the modern universe directly. They should agree, but they don't. This Hubble tension strongly suggests that our standard cosmological model, known as lambda cold dark matter, is incomplete. Something is missing from our equations. This missing piece could be a number of extraordinary things. Perhaps our understanding of dark energy is fundamentally wrong. The model assumes dark energy is a constant force, the cosmological constant that Einstein proposed. But what if it isn't constant? What if dark energy's strength has changed over time, or if it interacts with dark matter in some unknown way? This could alter the expansion history of the universe, throwing off the prediction from the early universe. Another possibility is that there exists a new type of neutrino or another unknown subatomic particle that was present in the early universe. This new particle would have affected how the cosmic microwave background looks, and without accounting for it, our reading of that ancient light is slightly off. The most radical suggestion is that our theory of gravity itself, Einstein's general relativity, needs modification on the largest cosmic scales. While it works perfectly within galaxies and solar systems, perhaps it breaks down when applied to the entire universe. Each potential solution is profound, and each would revolutionize physics. The Hubble tension is no longer a minor puzzle. It is the most significant clue we have that our current understanding of the cosmos is on the verge of a major breakthrough. It is a cosmic alarm bell ringing, telling us that we are on the cusp of discovering new physics, a revelation that could completely reshape our story of the universe from its first moment to its ultimate fate. Now, just when we thought we had a handle on the grand scales of cosmic violence and the intricate chemistry of life's building blocks, we turn our attention to a discovery so small it could fit on the head of a pin, yet its implications for biology and astrobiology are truly colossal. This story doesn't begin on the red sands of Mars, but in one of the most Mars-like environments right here on Earth, the summit of the Liquincaba volcano high in the Atacama Desert. At an altitude of nearly 6,000 meters, the air is desperately thin. The ultraviolet radiation from the sun is brutal and unfiltered, and the environment is so profoundly dry and cold it was long considered a place where nothing could possibly survive. It is a stand-in for the harsh reality of the Martian surface, a natural laboratory for testing the limits of life, and it is here, in this seemingly sterile wasteland, that researchers made a stunning find that blurs the line between life and non-life and could completely revolutionize how we search for evidence of biology on other worlds. They discovered the first known virophage adapted to a Mars-like extreme environment. To understand why this is such a monumental discovery, we first need to unpack what a virophage actually is. The word itself is a combination of virus and bacteriophage. A bacteriophage is a virus that infects bacteria. It's a predator of predators in a way. A virophage takes this concept a step further. It is a subviral agent, a microscopic parasite that is itself a virus, but it cannot replicate on its own. Instead, it hijacks the replication machinery of a much larger host virus. Imagine a wolf that doesn't hunt sheep, but instead attacks and incapacitates other wolves to steal the sheep they have already caught. That's the ecological role of a virophage. It invades a giant virus as that virus is in the process of infecting a single-celled amoeba or other host cell. The virophage then uses the giant virus's own viral factory, the cellular machinery it has commandeered, to replicate itself, often severely damaging or even destroying the giant virus in the process. It's a virus that preys on other viruses. Finding such an entity thriving in the punishing environment of the Aconcagua volcano is a paradigm-shifting event for several reasons. First, it reveals an unexpected layer of complexity in a microscopic ecosystem we assumed would be simple or even non-existent. The presence of a virophage implies the existence of a complete predatory chain. For the virophage to survive, its host giant virus must be present. And for that giant virus to survive, it must have its own host, likely a hardy, radiation-resistant microbe. This means that even in one of the most hostile places on Earth, there isn't just life struggling to persist. There is a dynamic, interacting web of life, complete with predators, prey, and even hyperparasites. The environment isn't just habitable for a few extremophiles. It supports a miniature, functional ecosystem. This discovery shatters our previous definitions of where life can and cannot exist. We have long used a simple checklist for habitability: liquid water, a source of energy, and certain key elements. The discovery of a virophage in such an extreme locale adds a new biological factor to that list: ecological interaction. Life, it seems, doesn't just cling to existence in isolation. Wherever it gains a foothold, it rapidly diversifies and creates complex relationships, even in the most forbidding landscapes. This suggests that a barren environment might not just be a sign that life never got started. It could be a sign that a pre-existing ecosystem has collapsed. The presence of these biological relationships could be a more robust biosignature than the presence of a single organism alone. This has profound and direct consequences for our search for life on Mars. For decades, our strategy has been largely focused on a direct hunt. Look for water, look for organic molecules, look for fossilized microbes. The discovery of the Aconcagua virophage suggests a new, more nuanced approach. We shouldn't just be looking for evidence of life. We should be searching for evidence of an ancient, or perhaps even extant, microscopic ecosystem. This changes what we consider a compelling target. Instead of just looking at ancient lake beds, we might also want to investigate sites of past extreme environments, like ancient volcanic regions or subsurface niches, where such a multi-tiered biological community could have once thrived. Crucially, it also changes what we look for. A virophage or its giant virus host would leave behind a very specific genetic or chemical signature. Our rovers and future sample return missions could now be programmed to hunt for the ghosts of these interactions, the molecular fossils of a predator-prey relationship that played out in the Martian soil billions of years ago. The implications reach even further into the very nature of viruses themselves. Are they truly alive? They can't replicate on their own, and they don't have a metabolism. But the existence of virophages shows that these entities are subject to the same evolutionary pressures: predation, competition, adaptation, that govern the rest of the biological world. They evolve, they form complex relationships, they can be the prey, not just the predator. This discovery paints viruses not as mere genetic hitchhikers or harbingers of disease, but as active, dynamic players in the ecology of any environment, integral to the flow of energy and genetic information. Finding a virophage on a Martian landform, therefore, wouldn't just be evidence of life, it would be evidence of a complex biological world, a microcosm that operated by the same rules of competition and survival that govern every other ecosystem we know. It suggests that if life ever did arise on Mars, it may not have simply fizzled out. It might have evolved, diversified, and created a hidden web of interactions that we are only now learning how to see. For decades, astronomers have listened to the universe in every wavelength of light, from radio waves to gamma rays, building a spectacular silent movie of the cosmos. But there was always a soundtrack missing, a deep, rhythmic beat that we knew must be thrumming through the fabric of space-time itself. We knew it had to be there, predicted by Einstein over a century ago, but it remained just beyond our perception until now. An international collaboration of scientists has finally tuned in, not to the violent crashes of individual events, but to the universe's permanent background hum, a chorus of gravitational waves so low and constant it forms the very base note of creation. This discovery wasn't made with a single telescope, but with a galaxy-sized instrument known as a pulsar timing array. Imagine the Milky Way as a vast pond, and surrounding it, a series of buoys bobbing gently in the water. In this analogy, the buoys are pulsars incredibly dense, spinning neutron stars that beam radio waves toward Earth with the metronomic precision of atomic clocks. For over 15 years, radio telescopes like NanoGrav in North America, the European Pulsar Timing Array, and others around the world have been meticulously monitoring the arrival times of these pulses from dozens of these cosmic lighthouses. Their hypothesis was profound. If a gravitational wave, a ripple in the fabric of space-time, passed between us and a pulsar, it would momentarily stretch and compress the distance the light had to travel, causing the pulse to arrive ever so slightly early or late. The signal from any single gravitational wave event would be too faint to detect, but the combined effect of a constant background hum of many waves would create a unique, correlated pattern of delays across the entire array of pulsars. It would be like sensing a gentle, persistent swell moving through the ocean by watching all the buoys rise and fall in a synchronized pattern. After years of patient data collection, that pattern has emerged from the noise. The timing deviations are minuscule shifts of only a few hundred nanoseconds over a decade of observation, but the signal is unmistakable. The universe is indeed filled with a low-frequency gravitational wave background, a resonant hum that has been ringing through space for billions of years. The most likely source of this perpetual vibration is a cosmic population of unimaginable scale, millions of pairs of supermassive black holes, each billions of times the mass of our Sun, locked in a slow, inward spiral at the hearts of distant galaxies. As these monstrous pairs orbit each other, they radiate away energy in the form of gravitational waves, filling the cosmos with their collective, low-frequency signal long before they finally collide in a moment of unimaginable violence. This hum is the sound of the universe's largest structures engaged in an eternal dance, a gravitational choir singing in a register we have only just learned to hear. Listening to this hum allows us to write a new history of the universe, one told not in light but in gravity. It provides direct evidence that galaxy mergers, the primary engine of galactic growth, are not just theoretical events from the distant past but are a fundamental and ongoing process throughout cosmic time. Every major galaxy, including our own Milky Way, is thought to have built its central bulge through a series of such collisions, each one funneling a supermassive black hole to the center to meet its partner. This background hum is the fossil record of that entire hierarchical merging process, confirming that our standard model of galaxy evolution is correct on the grandest of scales. It tells us that the universe is, and always has been, a dynamically evolving place where even the most massive objects are in constant, slow motion, drawn together by gravity in a process that takes hundreds of millions of years to complete. This discovery doesn't just confirm what we already suspected. it opens an entirely new window on the universe, the field of gravitational wave astronomy at the lowest frequencies. This is the opposite end of the spectrum from the high-frequency chirps detected by LIGO and Virgo from stellar mass black hole mergers. Where those are the sudden, violent cracks of a snare drum, this is the deep, pervasive resonance of a massive pipe organ. This new window allows us to probe the demographics of supermassive black hole binaries across time and space, understanding their masses, their separation distances, and their eventual merger rates. But even more excitingly, it allows us to test for other, more exotic sources that could be contributing to this hum. Could some of this signal come from cosmic strings, hypothetical defects in the fabric of space-time from the very first moments after the Big Bang? Might it contain echoes from the inflationary period, a time of ultra-rapid expansion when the universe was a fraction of a second old? The gravitational wave background is a new canvas, and we have only just begun to see the first brushstrokes of the physics that painted it. And just as we are learning to listen to the universe's gravitational hum, the James Webb Space Telescope turns its golden eye to a distant, flickering object and gives us a spectacular new way to see. In a universe that Webb is revealing to be filled with impossibly massive and mature infant galaxies, one discovery stands out not for its sheer size, but for its breathtaking clarity and the profound historical secret it has unlocked. This is the story of the Sparkler Galaxy, a system so far away we see it as it was just 4 billion years after the Big Bang, and yet it holds within its faint glow a collection of cosmic treasures that connect directly to our own home in the cosmos. The galaxy itself, officially known by the less poetic name of SDSSJ 1226 plus 2149.3, was first spotted in earlier surveys, but it was little more than a faint smudge. Its true nature was only revealed when Webb's unprecedented infrared resolution and sensitivity focused upon it, using a massive galaxy cluster in the foreground as a natural magnifying glass, an effect known as gravitational lensing. This cosmic lens amplified the sparkler's light, and in doing so, it resolved the smudge into something wondrous. Surrounding the central glow of the young galaxy were a dozen tiny points of light, like diamonds scattered around a golden pendant. The galaxy's charming nickname was instantly born. It was the Sparkler. The initial assumption might be that these sparkling points were individual stars within the galaxy, but that's not physically possible at such a staggering distance. Not even Webb can resolve single stars that far back in time. Another thought was that they might be small satellite galaxies in the process of being consumed, a common occurrence in the early universe, but the data told a different, far more exciting story. By analyzing the color and intensity of the light from these dots, astronomers made a stunning realization. These sparkles were not infant galaxies, they were ancient stellar cities. They were globular clusters. This identification was a monumental moment. Globular clusters are among the oldest known structures in the universe, dense, spherical swarms of up to 1 million stars that are bound together by gravity. Here in the Milky Way, we know of about 150 of them, and they are all ancient fossils containing stars that are nearly as old as the universe itself. They are the silver-haired elders of our galaxy, and their origins have long been shrouded in mystery. Did they form alongside the first galaxies? Did they form even earlier? The Sparkler Galaxy provided the first direct observational clue. Here, in a galaxy we are seeing in its relative youth, was a full system of globular clusters already in place, and their light suggested they were already incredibly old. This is where the discovery becomes truly mind-bending. The sparkler's light has taken roughly 9 billion years to reach us, meaning we see the galaxy as it was 9 billion years ago. But the redder, older stellar populations within the clusters themselves suggest that the stars in those clusters were already over 2 billion years old at that time. This means some of these clusters must have formed their first stars when the universe was only 500 million years old, a mere infant itself. We are not just seeing globular clusters in a young galaxy, we are seeing ancient globular clusters in a young galaxy. They were already venerable relics by the time the light we now see began its long journey to Earth. This discovery offers a completely new window into the very first chapters of galaxy assembly. The prevailing theory is that the earliest galaxies were built from the bottom up, growing by accreting smaller clumps of stars and gas and through violent mergers. The sparkler, with its system of massive, ancient clusters, appears to be a perfect snapshot of this process in action. It's as if we've caught a galaxy red-handed, just as it is in the process of collecting its globular clusters, perhaps by gravitationally capturing them from smaller, devoured dwarf galaxies, or by forming them in intense bursts of early star formation. These clusters are the building blocks, the foundational pieces that were later woven into the full galactic tapestry we see today. The significance of this extends all the way to our own cosmic doorstep. The sparkler galaxy is thought to be a distant analog, a younger version, of what our own Milky Way once looked like. By studying its captured system of clusters, we are essentially looking back in time at our own galaxy's formative years, watching how it acquired the ancient globular clusters that still orbit its center today. Each sparkle around that distant galaxy is a potential predecessor to clusters like Omega Centauri or Messier 13, allowing us to finally understand the origin story of these celestial relics. They are not merely ornaments, they are the surviving witnesses to the chaotic and violent construction project that built the great galaxies, and thanks to the sparkler, we can now begin to listen to their story. But if the sparkler galaxy shows us the ancient building blocks of galactic structure, our next discovery invites us to consider the possibility of entire worlds orbiting those very building blocks. Not planets around a star, but moons around a planet in another solar system. For years, the hunt for exoplanets has been one of astronomy's great success stories, with thousands of alien worlds now confirmed. Yet, a lingering question has remained: if planets are common, what about their moons? Could moons in other star systems, exomoons, also exist, and might some of them be habitable? The search has been fraught with false starts and extreme technological challenges, but now astronomers may have finally found the most compelling evidence yet for a true exomoon, and it is a world of staggering proportions. The candidate, known as Kepler 1708b, orbits a gas giant planet roughly 5,500 light-years from Earth. The planet itself, Kepler 1708b, is a Jupiter-sized world that orbits its sun-like star at a distance similar to Earth's orbit around our own sun. The suspected moon, however, is what truly defies expectation. Based on the data, this isn't a small, rocky body like the moons of our solar system. The evidence points to a behemoth, a moon with a radius approximately 2.6 times that of Earth. If confirmed, this would make it larger than the planet Venus, a world so vast it would fundamentally reshape our understanding of how moons can form and what they can be. Finding something so faint and distant next to a bright planet is like trying to spot a firefly buzzing next to a powerful searchlight from thousands of miles away. The method used to detect it, therefore, had to be incredibly ingenious. It relies on the same transit technique that has discovered thousands of exoplanets, carefully measuring the minute dip in a star's brightness that occurs when a planet passes in front of it. But for an exomoon, astronomers look for additional, even subtler clues within that dip. As a moon-bearing planet transits its star, the moon's gravity tugs on the planet, causing the planet to wobble slightly in its orbit. This tiny wobble can manifest in two key ways within the light curve data. First, it can cause the planet's transit to begin a little earlier or later than expected. Second, and more importantly, the moon itself may also transit the star, either just before or just after the planet, creating its own additional, much smaller dip in starlight. It is by meticulously searching for this combined fingerprint, a wobble in the timing and a secondary dip, that the signal for Kepler 1708b was found. hidden within the data from NASA Kepler Space Telescope. The challenges of confirming such a discovery cannot be overstated. The signals are incredibly weak, buried deep within the noise of the stellar data. Other astrophysical phenomena, such as star spots or the gravitational influence of a second, unseen planet in the system, can mimic the subtle signs of an exomoon. This is why the candidate remains just that, a compelling candidate requiring independent verification, likely with the powerful James Webb Space Telescope. Webb's ability to perform precise spectroscopic observations could potentially detect the atmospheric signature of the Moon as it transits, providing the smoking gun needed for confirmation. Should it be real, the implications are profound for the search for life beyond Earth. A gas giant orbiting in its star's habitable zone, like Kepler 1708b does, is not itself a candidate for life. But a large, rocky moon orbiting such a planet very well could be. Such a world, often called a habitable exomoon, could have a solid surface, hold onto a thick atmosphere, and potentially even have liquid water on its surface, all while being warmed by the reflected light and energy from its star and the radiant heat from its giant planetary host. The concept shifts the astrobiological paradigm, suggesting that the total number of habitable real estate in the galaxy might be far greater than we imagined, if we include not just Earth-like planets but also a vast population of large, life-bearing moons. The potential discovery of Kepler 1708b doesn't just add a new moon to a catalogue. It throws open a door, inviting us to imagine an entirely new class of world where the possibilities for life are as boundless as the cosmos itself. But if the discovery of the gravitational wave background gave us a new sense of the universe's grand, rhythmic dynamics, our next phenomenon pulls us into the heart of a single, catastrophic event, where the very laws of physics as we know them might have been momentarily suspended. We now venture into the realm of the deeply theoretical, to an idea so radical it proposes that the universe's most extreme conditions can give rise to a state of matter that defies all conventional description. This is the unparticle phenomenon, a concept that suggests that inside the unfathomable fury of a neutron-star merger, matter might stop behaving like a collection of distinct particles and instead transform into something entirely new and bizarre. To grasp what an unparticle could be, we first need to understand the limits of our current knowledge, encapsulated in the standard model of particle physics. This remarkably successful theory categorizes all the known fundamental particles and the forces that govern their interactions. It gives us quarks, electrons, neutrinos, and the Higgs boson. But for all its power, the standard model is almost certainly incomplete. It doesn't incorporate gravity, and it offers no explanation for dark matter or dark energy. The unparticle idea, first proposed by physicist Howard Georgi, is a bold attempt to step beyond this framework. He suggested that there could be a hidden sector of the universe governed by a different kind of physics where scale doesn't matter. In this sector, stuff wouldn't be made of well-defined particles with specific masses. Instead, it would behave as unparticles entities with no single mass, no fixed identity, and very strange properties. They wouldn't be particles at all in the way we think of them. They would be more like a continuous, scale-invariant substance. The obvious question is, where in the universe could such a bizarre state possibly exist? The answer lies in the most extreme environments imaginable. When two neutron stars spiral together and finally collide, they create a transient, ultra-dense object of almost incomprehensible density. For a fleeting instant, the matter at the core of this merger is squeezed to pressures far greater than those inside an atomic nucleus. Under these conditions, the quarks that normally make up protons and neutrons could be set free, creating a soup of deconfined quarks. It is in this exotic, short-lived quark-gluon plasma that physicists speculate unparticle behavior could emerge. The incredible energy and density might provide a portal, a brief window into that hidden sector of physics, allowing the matter to lose its particulate nature and exhibit scale-free, unparticle-like properties. This isn't just theoretical speculation, it could have observable consequences. The telltale signature of such an event would be written in the gravitational waves it produces. The merger of two neutron stars creates a distinctive chirp signal as the objects spiral inward, followed by a ring-down phase as the single merged object settles into its final state. If the merger product is a standard neutron star or a black hole, the ring-down has a specific, predictable pattern of frequencies. But if, for even a fraction of a second, the core of this object entered an unparticle phase, its properties would be radically different. It would oscillate and vibrate in a unique way, imprinted upon the gravitational wave signal. This would show up as a deviation from the expected signal, a subtle anomaly in the frequencies, and the damping of the ring down that our current models cannot explain. This is where a real event like JW170817 becomes absolutely pivotal. The gravitational waves from that historic merger were detected for over 100 seconds, providing a rich dataset. While the primary analysis focused on confirming the merger and its optical counterpart, a kilonova, a secondary and more speculative hunt is ongoing. Researchers are meticulously combing through that signal, particularly the post-merger data, searching for any tiny glitch, any faint whisper in the data that doesn't fit the conventional models. Finding even a hint of an unparticle signature would be a revolution. It would be direct evidence of physics operating at energy scales 1,000,000 times higher than anything we can create in particle colliders like the Large Hadron Collider. These cosmic collisions are nature's ultimate accelerator, and they are doing experiments for us that we could never hope to perform on Earth. The implications of such a discovery would ripple through all of physics. It would not only validate the existence of a hidden sector of reality, but could also provide a crucial link to understanding other profound mysteries, like the nature of dark matter. It might even offer clues about the unification of all fundamental forces. The unparticle is a testament to the power of human imagination, a hypothesis that pushes the boundaries of what we believe is possible. It reminds us that the universe's greatest secrets are often hidden in plain sight, encoded in the most violent and energetic events, waiting for us to learn how to listen to their deepest frequencies. Yet as we probe these theoretical extremes, we return to the stark reality of an observation that defies all expectation, a signal so bizarre and persistent it has become one of the most compelling mysteries in modern astronomy. Imagine a flash of radio energy so powerful it outshines an entire galaxy, lasting only a few thousandths of a second, and repeating not with any predictable rhythm, but in a chaotic, unpredictable stutter. This is the reality of fast radio burst 20,190,520 B, a signal that has shattered our neat categorizations and forced a complete rethinking of what could possibly generate such immense, focused energy across the cosmos. Discovered by the massive 500-meter aperture spherical radio telescope in China, FRB 20,190,520 B immediately stood out as an outlier among outliers. While other repeating FRBs had been found, this one was different from the very beginning. It was incredibly active, firing off bursts frequently and with wild variations in strength. But its most defining characteristic was discovered upon deeper investigation. It is permanently accompanied by a persistent radio source. This is a faint, constant glow of radio emission that is always there, humming along in the background even during the quiet periods between its brilliant millisecond flashes. This perpetual radio companion is a colossal clue, a sign that the engine powering these bursts is not just turning on and off, but is continuously active, a cosmic powerhouse that is always running at some base level, occasionally spitting out these incomprehensibly energetic flares. To add another layer of intrigue, this bizarre system is not located in a giant, mature galaxy like our Milky Way. It resides in a much smaller, more primitive type of galaxy known as a dwarf galaxy with an environment astronomers refer to as low metallicity. This is a crucial piece of the puzzle. In astronomy, metals refer to any element heavier than hydrogen or helium. A low metallicity environment means this galaxy is relatively poor in these heavier elements, which are forged in the furnaces of stars and scattered by supernova explosions. This suggests the galaxy is somewhat unevolved, a cosmic backwater that hasn't seen the level of star formation and stellar death required to enrich it with complex elements. This type of pristine environment is exactly where the universe's most ancient and massive stars are thought to form, providing a strong hint about the kind of object that could be behind these bursts. The prime suspect in this cosmic whodunit is a specific type of stellar corpse known as a magnetar. A magnetar is a neutron star born in the fury of a supernova, but endowed with a magnetic field so impossibly strong it defies human comprehension. To put it in perspective, a magnetar's magnetic field is a quadrillion times, that's a 1 with 15 zeros after it, stronger than Earth's. If a magnetar were located halfway between Earth and the Moon, it would effortlessly strip the data from every credit card on the planet. The prevailing theory is that the titanic stresses within the magnetar's crust, caused by this unimaginable magnetic field, can occasionally trigger starquake seismic events of such magnitude that they crack the star's solid surface and release vast amounts of energy, which we see as a fast radio burst. A persistent radio source could then be explained by a nebula of energetic particles swirling around the magnetar, trapped and energized by its monstrous magnetic field, creating a permanent radio glow. However, FRB 20,190,520b is so exceptionally active and energetic that it pushes the magnetar theory to its absolute breaking point. Could even a magnetar sustain such a high level of outbursts without tearing itself apart? This has led to other, more exotic proposals. Perhaps we are witnessing the aftermath of a recent supernova, with the expanding shell of debris from the explosion still enveloping the newborn magnetar. This dense, turbulent environment could provide the extra energy and the persistent radio source, acting as both a fuel and a lens for the bursts. Another, more speculative idea involves a peculiar type of black hole. An asteroid or other small body falling into a black hole with a strong magnetic field could, in theory, be shredded and generate a similar radio signature as it's consumed. The sheer strangeness of this object means that no single theory can yet claim to have all the answers. What makes FRB 20,190,520b so invaluable to science is that it isn't just one mystery. It's a package deal of cosmic anomalies. It combines a repeating burst pattern, a persistent radio source, and a specific galactic environment into one perfect laboratory. By studying this one system in exquisite detail, astronomers can test multiple theories at once. Does the persistent source vary in sync with the bursts, or does it change independently? What does the local environment immediately around the source look like? Each new observation peels back another layer, bringing us closer to understanding not just this one strange signal, but the entire population of these cosmic flashbulbs. It stands as a testament to the fact that the universe is always more creative than we are, capable of concocting phenomena that challenge our most fundamental assumptions and force us to expand our vision of what is possible in the vast and dynamic cosmos. And so we arrive at our final discovery, a revelation that brings our cosmic tour full circle, returning from the abstract frontiers of quantum reality and the violent hearts of distant galaxies to a small, icy moon in our own solar system, a place that may hold the answer to the oldest question of all. For years, Saturn's moon Enceladus has captivated scientists with its stunning secret. A global, salty ocean hidden beneath a shell of ice, periodically erupting into space through massive geysers at its south pole. The Cassini spacecraft gave us our first breathtaking views of these plumes, sampling them directly as it flew through the icy spray. We already knew these jets contained water vapor, organic molecules like methane and propane, and that the ocean below was warm, salty, and interacting with a rocky core, a recipe that ticks almost every box for habitability. But one critical ingredient remained elusive, a piece of the puzzle so vital that its absence cast a shadow of doubt over the moon's potential. That ingredient was phosphorus. In the chemistry of life as we know it, 6 elements are considered absolutely fundamental: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. You might remember them by the handy acronym CHNOPS. Phosphorus is arguably the most special of the bunch. It forms the backbone of DNA and RNA, the molecules that carry our genetic instructions. It is a key component of ATP, the universal energy currency that powers every cell in every living thing on Earth. It's essential for building cell membranes. Without phosphorus, life simply cannot function. It's the biochemical glue that holds the machinery of life together. And for years, despite all the other promising signs from Enceladus, phosphorus had never been detected. The fear was that it might be locked away in the moon's rocky core, insoluble and unavailable to any potential biology in the watery ocean above. Its absence was the strongest argument against Enceladus being a truly habitable world. That argument has now collapsed. Through a meticulous reanalysis of the data collected by Cassini's cosmic dust analyzer, scientists have done the impossible. They have found the fingerprint of phosphorus. And they didn't just find a trace amount. The data suggests the concentration of phosphorus in Enceladus's ocean could be hundreds of times greater than it is in Earth's oceans. This isn't a missing ingredient, it's an ingredient available in abundance. The discovery came from identifying compounds called phosphates within tiny grains of rock and ice that were ejected from the ocean deep below and eventually encountered Cassini's sensors. These grains, upon closer inspection, were found to be rich in a phosphate mineral called sodium phosphate. On Earth, this same compound is highly soluble in water, meaning it readily dissolves and becomes accessible for biological processes. The conditions on Enceladus are alkaline, carbon-rich ocean churning against a rocky seafloor, appear to be perfectly suited to leach phosphorus out of the core and into the water, creating a veritable soup of prebiotic material. This single finding transforms Enceladus from a maybe into the single most compelling known habitable environment outside of Earth. It now has all 6 of the fundamental biological elements. It has liquid water, it has a source of chemical energy from hydrothermal vents on its ocean floor, it has the right chemistry, it has stability with an ocean that has likely existed for billions of years. The checklist is complete. This doesn't mean we have found life on Enceladus. That discovery remains for a future mission. But it does mean we now know, with a high degree of confidence, that the moon possesses every single ingredient and condition that we believe are necessary for life to arise and persist. The implications for astrobiology are nothing short of seismic. Of all the potential habitats in our solar system, the subsurface oceans of Europa and Ganymede, the ancient lakes of Mars, Enceladus now stands alone as the most accessible and the most promising. Its genius is that it delivers its ocean to us, spewing samples of its inner world out into space where a spacecraft can simply fly through and collect them. We don't need to drill through miles of ice, we just need to catch the snow. This makes it the prime target for the next generation of life-seeking missions. Imagine a probe designed to orbit Saturn, making repeated passes through these icy plumes, collecting thousands of particles and analyzing them not just for chemistry, but for direct signs of biology, perhaps for complex organic structures or even amino acids that show a preference for one-handedness over another, a potential signature of life. The dream of finding a second genesis of life, of answering whether we are alone in the universe, may well rest on this small, gleaming world of ice and rock. a place that has quietly assembled all the pieces of the puzzle and is now, quite literally, shouting them into the void for anyone willing to listen. And so our journey through the cosmos comes to a close, a tour that has taken us from the shockingly local to the edges of the observable universe and back again. We've witnessed supermassive black holes on the run, weaving trails of newborn stars across the void. We've stood before cosmic structures so vast they defy the very laws that should govern them, and we've held in our hands the very building blocks of life, delivered from an asteroid and a moon within our own solar system. We've seen stars that smoke and fade, heard the bass note hum of colliding galaxies, and even probed experiments that suggest the present can reach back and shape the past. Each one of these 25 discoveries is far more than a new entry in a catalogue. They are profound shifts in our understanding. They are the universe politely, and sometimes not so politely, informing us that our textbooks are incomplete. They prove that the cosmos is not a static museum exhibit but a dynamic, evolving, and violently creative arena where the rules are still being written. The sheer weirdness on display, from orphan radio circles to white dwarf pulsars, is not a bug in the system, it is the system. It is the sound of nature operating at its most fundamental and extravagant level, constantly surprising us with its ingenuity. This relentless push against the boundaries of knowledge is the very engine of science. It's the thrilling process of being proven wrong, of having a beautiful theory slain by an ugly, inconvenient fact, because that is how we get closer to the truth. These mysteries are not roadblocks, they are the road signs pointing us toward the next great revelation. They invite us to stay curious, to keep looking up, and to keep questioning everything we think we know. So we leave you with this thought: the night sky will never be the same. Behind every familiar star now lies the potential for a rogue black hole, a hypervelocity exile, or a nebula hiding a recursive secret. The darkness between them is no longer empty but filled with the gravitational echoes of cosmic mergers and the faint, persistent glow of our galaxy's own massive atmosphere. The universe has shown us its cards, and they are wilder than we ever dared to dream. Now we have to ask, which of these 25 phenomena completely rewired your brain? Was it the universe's background hum, the quantum experiment with ancient light, or the icy moon that has everything needed for life? Let me know in the comments which discovery captivated you the most, and don't forget to like and subscribe for more deep dives into the cosmos's greatest mysteries.